A fan blade does not create pressure because it merely looks steep. Performance comes from the angle between the blade chord and the air the rotating blade actually meets. In this video, we will separate geometric pitch from aerodynamic angle of attack, then show what changes when pitch is swept at one fixed speed. Start with the real axial impeller. Pitch, or installation angle, is a geometric setting measured between a defined blade reference such as the chord line and a defined rotor plane or axis. The convention must be written down. A photograph can show blade form, but it cannot by itself reveal the operating angle of attack. Now build the velocity triangle at one radius. The blade has tangential speed u, equal to angular speed times radius. Air has an axial component Va, and it may also have swirl. The blade experiences the relative velocity W, formed by subtracting blade motion from absolute air velocity. W, not the camera view, sets the incoming flow direction. For this video, beta is the local blade installation angle and phi is the local relative flow angle, both using the same reference. The angle of attack alpha is their difference. Change RPM, airflow, inlet swirl, radius, blockage, or system resistance, and phi changes even though the metal pitch remains fixed. That is why pitch and angle of attack are not interchangeable. At a useful positive angle of attack, pressure is lower on one side of the blade and higher on the other. The resulting aerodynamic force can be resolved into a useful axial component and a tangential component that demands motor torque. Lift helps create pressure and flow, drag and induced losses raise shaft power and heat. Increase pitch at fixed RPM and the blade initially turns and loads the air more strongly. But the benefit is not unlimited. When angle of attack becomes too large for the local section and flow condition, the boundary layer separates. Lift stops increasing predictably, drag rises, wakes thicken, and rotating stall or unstable flow may appear. Too little pitch creates a different mismatch. The blade may be lightly loaded, producing less pressure and often less airflow against the same system. The motor may draw less power, but the fan may fail the duty point. Efficient design is not the smallest angle or the largest angle, it is a matched spanwise loading at the required operating point. Radius makes the problem three-dimensional. Because U equals omega times radius, tangential speed is lower near the hub and higher near the tip. Axial velocity and swirl can also vary across the annulus. A twisted blade changes local beta from root to tip so each section approaches its intended angle of attack instead of forcing one angle everywhere. Now hold speed, diameter, blade count, tip clearance, density, and test setup constant, and sweep pitch. Measure volume flow, static or total pressure with the boundary clearly named, electrical input, torque if available, sound spectrum, motor temperature, and stability. Plot every result at the same system or standardized test boundary. The expected trends are coupled, not guaranteed straight lines. A moderate pitch increase may move the fan curve toward more pressure and flow, while power and noise also rise. Beyond the useful region, separation can flatten pressure, increase broadband and tonal noise, raise torque, and reduce efficiency. The exact knee belongs to the real blade and operating condition. Real Longwell axial fan footage gives us physical blade, hub, shroud, tip clearance, and manufacturing context. Test room imagery shows where repeatable aerodynamic measurements belong. Neither source proves a universal best angle, and a drawing angle cannot be copied across diameter, speed, blade section, motor, guard, or system resistance. For an OEM decision, release the reference convention, hub and tip geometry, blade section and twist, target curve, operating envelope, RPM, density, tip clearance, guard and duct interfaces, motor limits, sound target, and test method. Then validate several pitch candidates instead of trusting one free air point. Contact Longwell.